Greek letters, alpha, beta, gamma, delta, are used to describe the proximity of carbon atoms relative to some specific group. In this chapter, we're going to look at carbon atoms relative to a carbonyl group. So here's our carbonyl, and one carbon over we call the alpha carbon. 2 carbons over are the beta carbons, 3 carbons over are the gamma carbons, and 4 carbons over would be the delta carbon. And this chapter primarily explores reactions that involve the alpha carbon. Alpha protons are the protons attached to the alpha carbon. And when I use the word proton, I mean hydrogen. So here, if we start with this ketone, acetone, we can convert that into something called an enol, or we can convert it into something called an enolate. So the word enol, E-N-O-L, indicates that there's a carbon-carbon double bond, that's where the En comes from, and an alcohol group, that's where the Ol comes from. The enolate is simply the enol, but it's been deprotonated. And most reactions that we're going to discuss will proceed either via an enol or an enolate form. And then we can react the enol or the enolate with some electrophile and add a group to that alpha carbon. In the presence of acid or base, a ketone or aldehyde exists in equilibrium with its enol. So this would be the ketone form, and this would be the enol form. The ketone and the enol are what we call tautomers of each other. So they are not resonance structures because they don't differ in just the placement of electrons. The atoms are actually connected differently. So here, this carbon has 2 hydrogens, but one of those hydrogens in the enol form is now attached to the oxygen. And that pi bond has moved to be between these 2 carbons. Now this equilibrium generally favors the ketone form. There are exceptions such as 1,3-dicarbonyl compounds, which favor the enol form at equilibrium, and that is due to conjugation and intramolecular hydrogen bonding. So here, when we convert this ketone into its enol form, we get this structure, and the hydrogen on this oxygen can actually form an intramolecular hydrogen bond, which stabilizes the entire structure. And also, this pi bond is in conjugation with that double bond, adding additional stability. Phenol is an example where the enol is vastly favored over the keto form at equilibrium. So here, this would be phenol. This is the keto form. The phenol is highly, highly favored because it is aromatic, whereas the ketone form is not. So how do we go mechanistically from the keto form to the enol? Well, it depends upon whether we're in acid or we're in base. So if we're in acid, the first thing we're going to do is protonate the carbonyl oxygen with acid. Now that forms a resonance stabilized cation. So if we draw it in this resonance form, then we can have a molecule of water do a proton transfer to form the carbon-carbon double bond to get to the enol. In base, those 2 steps are reversed. The strong base will deprotonate the hydrogen on the alpha carbon to form an enolate, and then those 2 electrons form the carbon-carbon double bond, simultaneously breaking that pi bond, and then that oxygen gets protonated with water. It is safe to assume that some fraction of a ketone or aldehyde will exist in the enol form. And the alpha position of an enol is nucleophilic. And that's easy to see when you draw the resonance structure of the enol shown here. In the presence of a strong base, such as LDA, which I'll talk about in a bit, an enolate can form, which is the charged conjugate base of the enol. So here we're deprotonating the alpha carbon. Those 2 electrons go onto that carbon. But here we're going to have a stoichiometric amount of the strong base. So the enolate will not get protonated to form the enol. It's going to stay as the enolate. And the enolate is much more nucleophilic than the enol because it has a negative charge. There are two sites of reactivity for the enolate, the oxygen and the carbon. However, everything we're going to see in this chapter involves the carbon acting as the nucleophile. Alpha protons are the only acidic protons in an aldehyde or a ketone. When you go to the beta or the gamma carbons, those hydrogens are not acidic enough to be deprotonated in any pragmatic fashion. And the reason for that is that the resulting carbanion is not resonance stabilized. When figuring out what base you can use to form an enolate, it is useful to know the pKa of the proton you're trying to remove. So for a ketone, the pKa is going to be around 19.2. Here we have this ketone about 18.3, and here this aldehyde about 16.7. When the pKa values of the base conjugate acid and the starting material are similar, so here for this aldehyde, the pKa of the alpha proton is 16.7, and the pKa of the conjugate acid of the base is 15.9. So those are similar. When the pKa values are similar, then both the starting material and the products will be present in significant amounts. If you want to irreversibly and completely form an enolate, then you need to use a strong base such as a hydride or LDA, also known as lithium diisopropyl amide. So if we think of this as just an acid-base reaction to determine how much the reaction lies to the right or to the left, you just compare the pKa of the starting acid and the conjugate acid. So here the starting acid, this aldehyde, that hydrogen in red, has a pKa of 16.7, and then the conjugate acid of the base, so here's your base, has a pKa of 36. So in acid-base chemistry, the equilibrium always favors the weaker acid, and this is weaker by almost 20 pKa units. So this is going to essentially be all product and no starting material. When you have two carbonyls with a carbon connecting them, the hydrogens on those carbons are much more acidic. So for example, the pKa of the hydrogen in red there is 9 versus the hydrogen we've been looking at. And this increased acidity is due to the increased stability of the resulting enolate. So remember, the more acidic something is, the more stabilized its conjugate base. So since this base is stabilized by these different resonance structures, so that increased resonance stability, the starting acid must be more acidic. And these are acidic enough to be irreversibly deprotonated with an alkoxide, so such as ethoxide. So here it would be overkill to use sodium hydride or LDA to form the enolate irreversibly. It's important to know what base to use because you need to know, are you irreversibly forming the enolate, or do you want to have both enolate and starting material in your flask? Because different types of reactions require different conditions. So for example, if you have a ketone and you use hydroxide or alkoxide, you're going to have both the enolate and the starting ketone present at equilibrium. However, if you use one of those super strong bases like sodium hydride or LDA, you're going to only have the enolate. And then if you look at the dicarbonyl, well, you're going to have complete enolate formation with a base like hydroxide or ethoxide, and you could use LDA, but it is certainly not necessary. Under acidic conditions, ketones and aldehydes undergo alpha halogenation. So here we have a ketone, and this is the alpha carbon, and we're adding a halogen to the alpha carbon, hence alpha halogenation. And you can do this with chlorine, bromine, and iodine, not with fluorine. And since we're in acidic conditions, you can be sure that the enol, not the enolate, is the reactive intermediate. So for this mechanism, the first thing we do is form the enol through the mechanism you saw previously. And then the enol is going to attack the halogen. So electrons move back down, and the pi bond reaches out to bond with the bromine atom. simultaneously breaking the bromine-bromine bond, and then a final proton transfer gives you the product. When you have an unsymmetrical ketone, you can get two different enols formed, and halogenation will occur faster at the more substituted carbon. So here we have this carbon on the right, and then this carbon on the left, and notice that halogenation occurs more quickly at the carbon on the right. So this will be your major product. And the reason for this is that the major product results from the more stable enol, and this goes back to our understanding about substitution on alkenes. The more substituted an alkene, the more stable it is. The Hell-Volhard-Zielinski reaction brominates the alpha carbon of a carboxylic acid. So here's the alpha carbon, and we've added a bromine atom. And this mechanism is believed to also proceed through an enol, but first the acid is converted to an acid halide, which then forms an enol and is halogenated, and then that acid bromide is hydrolyzed back to the carboxylic acid. Alpha halogenation can also be done with base, and under basic conditions you form an enolate, which then reacts. So here's your enolate. That's going to react with the halogen to add your halogen to the alpha carbon. The issue with using basic conditions is that you can keep adding halogens, so you end up with polyhalogenation, which you may not want. And then once the ketone is brominated the first time, it forms an enolate even quicker the second time. This can be taken advantage of with the haloform reaction. So in the haloform, if you have a methyl ketone, so on one side you have a methyl group, you can convert that into a carboxylic acid. And this is going to proceed through multiple halogenations. So you essentially halogenate 3 times. So now you end up with 3 bromines on that carbon. Now this whole thing is now a good leaving group. So then the hydroxide comes in, attacks the carbonyl carbon, forms the tetrahedral intermediate, which then collapses, kicking off CBr3 as the leaving group. The resulting carboxylic acid would then get deprotonated to form bromoform, which is why this is called the haloform reaction. If you used chlorine, you could form chloroform, iodine, iodoform. Now this works best if you have a methyl on one side and then something on the other side without alpha protons, because then there's no competition about which alpha proton you're going to remove. So the final reaction in this video is the aldol reaction. When an aldehyde or a ketone is treated with hydroxide, you get an equilibrium where you have some of the enolate and some of the starting ketone or aldehyde. With those conditions, you can do what's called the aldol addition reaction. So this got the name aldol because you end up with an aldehyde and an alcohol product if you're using an aldehyde starting material. Now you can also use a ketone, and people still typically call that an aldol. So for in base, you form an enolate with, for example, hydroxide, and then that enolate attacks a second molecule that isn't in the enolate form. Because in your flask, you can think of it as having half the starting material as it is, and then half of the starting material looking like its enolate form. So the enolate form attacks the normal form of itself. So here we attack the carbonyl carbon, kick the electrons up onto oxygen. We get to this intermediate, which then gets protonated with water. And so this would be our aldol product. So the new bond that was formed is this carbon-carbon bond right there. So here is an animation of the aldol. So the hydroxide removes an alpha proton from one of the aldehydes, and now that enolate attacks a second aldehyde, And then that O minus will get a proton from water. And then there's your aldol product. You can also do the aldol with acid catalyzed conditions. So with this, the first thing you would do is protonate the carbonyl oxygen. And then that's going to form the enol. And then the enol will attack a second molecule of the protonated aldehyde. And then a final proton transfer gets you to your aldol product. For most simple aldehydes, the aldol product is favored. However, for ketones, the aldol product is usually not favored. If you do the reverse process, this is called a retroaldol, and the mechanism is simply the opposite of the aldol addition. When we use the word condensation, we're referring to the loss of a water molecule. And when an aldol product is heated, an equivalent of water can be lost from it to form a condensation product. So here we have the alpha and beta carbons. When we heat this OH and that one of those two hydrogens gets lost, and you end up with a double bond between the alpha and beta carbons. And aldol condensation occurs when you perform the aldol at high temperatures. So here we have the aldol addition, but if you do that at high temperatures, it will likely proceed to the unsaturated aldehyde, so it will go through the aldol condensation as well. And the driving force for this is that you get this conjugation between that double bond and that double bond. So for the mechanism, you have the aldol addition, which you've already seen, and then you have elimination of water. If we're in base, you can deprotonate that alpha carbon to form the enolate, and then that lone pair can form the carbon-carbon double bond, kicking off hydroxide. Because aldol condensation is favored, a lot of times it's very difficult to isolate the aldol addition product. So for example, in this reaction, you only get this. You can't get any of the aldol addition product, even though it proceeds through that intermediate. This will just quickly go on to form a double bond between the alpha and beta carbons right here. So we're going to lose that OH and one of these two hydrogens on the alpha carbon. The yields for condensation are typically much greater than the yields for the addition. So where before I mentioned that this addition reaction would be low yielding, if you simply go from 10 degrees to 100, so if you just heat this up, you can get a good yield of the condensation product. Now, up to now, we've been looking at the same aldehyde or ketone reacting with itself, where we think of half of the molecules being in their enolate form, the other half being in the aldehyde or ketone form, and those reacting together. If you have different aldehydes reacting together, that's called a crossed aldol reaction or a mixed aldol reaction. So in this case, one would be the enolate, one would be the accepting aldehyde. And with this, you can get a variety of products. So if you took these two aldehydes, you could have both of the ones in red forming an aldol. You could have both in blue forming an aldol. Or you could have the aldehyde in red acting as the electrophile and the aldehyde in blue acting as the nucleophile, or vice versa. So there's a whole bunch of different products you can get out of a crossed aldol reaction. Because of that, these reactions are really only practical if you can force the aldehydes to only act in one of the two roles. So for example, if one of the substrates is relatively unhindered and doesn't have alpha protons, then it cannot be the enolate, it can only be the electrophile. So here, if we had formaldehyde, it doesn't have an alpha carbon, so it could not be the enolate, so it can only be the electrophile, and then this could be the enolate nucleophile. So here we'd form the enolate, it would attack the carbonyl carbon, and then upon protonation you would get this aldol product. So here is the new bond that you formed. Here's another example where this doesn't have any alpha protons, so it can only be the electrophile. So you would form the enolate of this, it would attack the carbonyl carbon, and then upon protonation you would get this aldol addition. However, with heat, that's not going to be isolated. We're going to go all the way to the condensation product. Another thing that you can do is something called a directed aldol, where you use a really strong base. So with this, you start with the molecule you want to be the enolate. For example, acetone. You add your super strong base, and it completely converts that into the enolate. Then once that is formed in your flask, then you would add the other partner that's going to be the electrophile. And by doing this, you're forcing them to either have the role of the enolate or the role of the accepting electrophile. You can also do an intramolecular aldol, where you form the enolate of one of the ketone or aldehyde groups, and it attacks the other group in the same molecule. So here, if we formed an enolate on this carbon, it could attack the carbonyl of the other group within the same molecule. Importantly, we only typically get 5- and 6-membered rings this way because those rings are very stable. They don't have very much ring strain. So smaller or bigger rings would not typically form. Okay, test yourself. So for this one, how many alpha protons does the carbonyl below contain? Number 2, which of the following reagents produces an irreversible enolate formation? And I should clarify for a ketone or an aldehyde. So for example, for acetone. For this, look at this starting ketone. You're going to react it with acid and bromine. And what is the major product? A, B, C, or D? Now this one is an aldol reaction. So this aldehyde shown here is going to react with itself in an aldol. So you want to make the enolate of one and have it attack the aldehyde form of another and see what product you get, A, B, C, or D. Now the product shown here is the result of a cross aldol. Can you figure out what 2 starting materials you must have used to get to this cross aldol? And that is it for this video. Thank you for watching.